Hello everyone, Namaste. I am Ramnath who would like to share with you the VLSI design topic, probability density and its impact on design yield. This is part 4. Other parts have already been shared with the same title. Feel free to ask any question or give any comments. Thank you. The electronic chips are going into commercial product lines, automotive product lines, critical care systems, and also into space systems. So we need to be very clear about the quality of the chips because the defects in the chips will drastically affect the overall system. So if you observe in the recent 2022, the production of the cars are close to 85 millions. These are all produced by around 40 countries. So yeah, and we also know that each car or light vehicle will contain around 5,000 to 8,000 chips. So the reliability of the system, that means car or trucks or any other vehicle, will be very key. So none of the chips should actually fail. So given that, we need to know that the reliability of the entire chip will affect the warranty and the brand name of the vehicle. So let us consider a situation wherein a car automaker is producing around 25,000 cars per day. This is not quite unreasonable because there are countries which are producing close to 8 million cars per day, per year. So the as we also know that around 5,000 chips are present in a car, and this will vary if the car becomes an autonomous vehicle, and EV vehicles are also adding more electronics into the system. So the total chips in all cars produced equal to 2500 into 5000 chips per day. So if there is one DPPM, that means like one defects in a chip, that means like one defects per parts per million. That means like one chip of 1 million produced have a defect. Then let us see what will happen. Okay, that is mentioned as DPPM. So then you will understand that the number of defective cars will be 2000, 25,000 into 5,000 by 1 million. This is per day. So 125 cars per day will be defective. That means only if we have a DPPB, that means like defective parts per billion, then the number of defective cars will be 0.125 per day. That means which translates to 46 defective cars per year. This is somewhat reasonable, but hence 1 DPPM is also not acceptable. So for the total volume production of the chips, we need to ensure that the DPPM value should be around 1 DPPB. Okay, here there is some gross assumption is made that the 8 million or 9 million cars which are produced by this automaker all are produced from the same fab and all belong to the same chip. So this is slightly kind of like unrealistic, but let us think that this is what it is. So coming to the other one, we want to mention that failure analysis, after figuring out the number of defective pieces, it is observed that the majority of reliability defects are actually process oriented. So the fabs need to take the majority of share in improving their processes. So to give a small picture of what the defect and how it will affect, so here Let us consider the following situation. Here there is a metal line and there is a defect. Okay, so here due to some impurity landing on this metal line because of some imperfections in the process or steps being performed through, then there is a break in the metal line. This definitely can be caught through the several stuck at and one or stuck at zero kind of fault coverages most of the times. Okay, so this is why it is called as a killer defect. Definitely it can be found, and there is a high chance that this will not be popping up at the customer end. Very unlikely. But there are some defects. Okay, so there are some defects here which will not affect any of these metal lines. So even if it falls here, this is no longer a threat. So this is a no issue. But coming to this one, there is a defect such as this. It is falling on the metal line, and if you observe, it has only eroded the metal line partially. So we don't know how much it will affect over a period of time. So this is a latent defect. This sometimes, if it crosses the crucial burn-in and other lifetime time testing scenarios, then if it crosses, then it will be going into the customer end, and it will be part of the system. That is when the chip defects become very critical. So these kind of things we need to avoid, and for that the fab defects also need to be reduced. Aside to that, we also need to ensure that during the design implementation and design selection, all these things we need to improve the robustness. We will figure out those things more in the coming slides. As evident from the earlier discussion, the impact of the chips will affect the overall yield of the system. So let us understand different processes involved in the chip making. As evident, semiconductor wafer fabrication, soft design implementation, silicon testing and silicon validation, these are all major processes involved, and all these processes must be executed using industry standard and benchmarked business processes, so that we will achieve high yield. As we know, all these processes are serially executed, and their overall yield can be obtained using this formula. So process 1, say semiconductor wafer fabrication, process 2, design implementation, like that. So the overall yield is calculated as the multiplication of these 4 processes. We need to know that we don't need to keep one of these processes, say Y3 can be exorbitantly higher than Y1, Y2 and Y4. So by doing that, we will not achieve the overall yield very high value. So this point we need to remember. So we need to ensure that all these 4 processes should be performing almost at the same, slightly 1 or 2 maybe can be slightly higher. So coming to the other how these processes are again have yield can be calculated, we need to know that whether there are any sub processes exist in this system. So definitely each process will have sub processes. So all those sub processes need not be serially executed. Some of them will be executed in parallel, Sometimes the silicon testing or silicon validation will have some processes which will have interdependent processes. So interdependence means that the change in one part of the sub process will impact the other sub process. So that is what it means. Here all these sub processes are interdependent. It need not be the only way. Okay, and the sub processes involved in the, say, soft design implementation can be having parallel sub processes also. So and some of them will have series and parallel combinations also. So sub processes, what I mean is, say, in the case of soft design implementation process, synthesis and DFT implementation, placement, clock tree, routing, physical DRC, and physical verification. All these sub processes can be serially executed or serial parallel executed. All these those possibilities exist. So we need to know how all these sub processes are linked. Based on that, we need to arrive at the yield of that process. So from there, we need to arrive at the overall process yield. So we need to know also that each of the system which can be either auto grade or commercial product, or it can be used in a space system. Based on that, the chip initial conditions of operation differ. So we need to ensure that these initial operating conditions, whether it is PVT or any other conditions, those things make a big difference in the overall yield of the system. So all these things are interrelated, and hence we need to be ensuring to keep them at a high quality. Failure of the chip depends on the use case of the system. So as a use case of the system mainly affect the voltage, temperature, slow load conditions, and aging of the chip. However, it indirectly affects the process of the chip. So we need to be aware that what type of product, the end product it is, where the chip is going. So if we understand first, the chip will have several instances nearby. So whatever be the voltage from the low voltage low dropout regulator or the external battery, whatever it supplies, that is not what it is reaching the specific instance of the design, because of the IR drop associated. So there will be some difference in the voltage seen. So and because of the variability of the battery, sometimes there can be slight swing, and due to the power switch cells and other things also, there can be changes in the voltage seen by the specific instance of the gate. And these devices, since they are present at different locations of the chip, same cell, so different instances will be experiencing different voltages. Hence we need to account for their specific instance based voltage, and then we need to make the design robustness accordingly. In the same way, temperature also differs based on the operating conditions. So whether it is used under the hood of the car, or it is used in a cold atmosphere, or it is working in a hot environment, based on that the nominal temperature will differ. That means like there will be differences to the normal temperature. So it can vary from -40 degrees to plus 150 degrees also. So based on the auto grade, 0, 1 or 2, so the temperature, maximum temperature, either it is 85 or 105 or 125, all that 150, all that will be differ. And slow load conditions will also change based on the design mode considered. So sometimes if there is a low voltage operation, sometimes they will be operating with a low frequency. So hence the design may be operating at high slows. So at that time there will be it will be more than the nominal value, and we need to ensure that design robustness will be taken care of while changing changes happen in these items, including aging. Aging also differs with the normal commercial product, say mobile phone and all. Sometimes they will ensure only 4 5 years and all. In the case of auto products, they will ensure 10 to 15 years. And in space applications, aside to the age, it will also need to be radiation hardened and all. So there are different constraints which will come into play, and hence the BTI degradation and HCA degradation, all those things will change. So based on the use case of the system, the design robustness and the validation of the system will also change. So we need to ensure that when we are taking through the different processes, the use case of the system is taken into consideration and appropriate measures are taken. And in the same way, the process also need to be tweaked based on the use case of the system so that the high yield will happen. We will know a little bit more in the coming slides. Process distribution and process capability index, CPK. To know more about the semiconductor wafer fabrication, which is part of the chip development, we have already understood how the different metrics of the integrated circuit, like drain source current or sidewall angle or width of a MOS, such as niche metric of the uh, device. So to know about that, we need to know that the distribution of that should be within some lower control limit and upper control limit. And further, this lower specification limit should be less than the lower control limit. Similarly, upper specification limit should be greater than the upper control limit. So this is for the 3 sigma process. When we have polled the data of this metric at different times, we will see that there will be a slight distribution because of the random variables coming into play. So we will know that the distribution of a 3 sigma process will be ranging from -3 sigma to +3 sigma, and here it is. And we will also know that the corresponding CPK value will be close to 1.0. And if we want higher uh, uh, quality, then the distribution should be limited to a small and narrow limits. So hence, if you observe that the process capability index will go to 2.0. So we need to ensure that the LCL should be less than the mean minus 6 sigma, and here now upper control limit should be greater than mean plus 6 sigma. So this is what we need to ensure to get higher quality and low defect rate. So if you observe here, for different sigma values, the different DPPM are mentioned here, and the corresponding CPK values are also mentioned. So for 6 sigma, the value is 2 DPP B. B stands for billion. So, and the CPK corresponding to that is 2.0. So this is all two-sided distribution, and if it is one-sided distribution, it will be the DPMO will be less than this one by 2. So the 3 sigma value for the CPK value is 1.0. Thus, we need to improve the manufacturing fab processes also to achieve higher quality. So low defect rate will happen And for that it is the their distribution will also be different. That means like current 3 sigma processes whatever are being run cannot be simply taken as will work for the 6 sigma. So the chip development, all these processes also to be of high quality and close to 6 sigma to ensure that they are meeting the standards of the low defect rate. Let us consider some row houses in a city where they exist on the roads. So if you observe carefully, some of these houses exist on one road and such as these also, but this house exists on both roads here. So that is why this is called corner plot or corner house. Sometimes it is also called corner lot because it is also part of some space. So this same concept is used even to designate the processes when we are dealing with different um, metrics of a NMOS and PMOS channel devices. So let us consider this belong to drained source of a NMOS transistor, and let us consider this to drain to source P channel transistor. So here the drain to source will be less because the devices are slow, and as we go along the drain to source current of NMOS will increase. In the same way drain to source current will be less here, and as we go along the drain to source current will be more. So this portion, the drain to source current of both NMOS and PMOS will be less. So we consider this as slow to slow, slow for NMOS and slow for PMOS to signify this location. In the same way, different corner also are calibrated accordingly. So let us go more into this part. Let us find out what are corner lots. Corner lots are sometimes called as split lots or skewed lots or matrix lots. They are all one and the same. So corner lots usually contain wafers which have been skewed by the fab to get different corners. So the process parameters are carefully and deliberately adjusted in these wafers so that they correspond to different amounts of sigma. So based on whether it is 3 sigma or 6 sigma in some cases, the wafer will contain 3 sigma of NMOS and 3 sigma of PMOS, or 2.5 sigma of NMOS and 1.5 sigma of PMOS, like that. Different wafer sigma conditions will exist in this corner lot. So one group of these corner lot are called corner lots. So sometimes we also will find that the wafer will contain a fraction of the sigma. Why this is done is basically to mimic the corner chips which usually exist in the volume production. So we will figure out now what how these corner lots are created. If you see here the distribution of the drain to source current of NMOS, distribution of the drain to source current of PMOS. So here the value of drain to source current is less, here the value of drain to source current is more. This is the nominal value. In the same way, small here, high here, and nominal. So here the same thing is represented, drain to source of PMOS, drain to source of NMOS. So if you see their distributions, and we will know that the drain source current of NMOS, here it is high, drain source in current of PMOS, here it is high, which will be represented by this part of the corner lot. So here in this corner lot, if you observe, this belongs to fast condition. That means like NMOS is fast and PMOS is also fast. So in this way, so the wafer will be created accordingly. So the process parameters will also be tuned accordingly. In the same way, if you observe, this part will correspond to slow of NMOS, slow of PMOS, that is this one. And the way this wafer is constructed by the fab accordingly. And we need to remember that these two are different wafers. Okay, in the same way, nominal corner, here this wafer is different, and in this same way, this belongs to fast condition of NMOS, slow condition of PMOS. This one, this wafer is different. In the same way, here fast condition of slow condition of NMOS, fast condition of PMOS. Here also 2.5 sigma of NMOS and 1.5 sigma of PMOS. This one. In this way, this wafer is created. In the same way, for different sigma conditions, if it is 6 sigma, 4.5 sigma of NMOS and 5.5 sigma of PMOS can be created. So since these corner lots are all different, each corner lot is different in this one, and hence these corner lots are having different wafers. So this is purposefully deliberately created. Why they are deliberately created is because, and we need to know that aside to just one type of NMOS and PMOS, we also need to remember that in soft design there will be several types of NMOS and PMOSs. For creating standard cell logic libraries, or for memories, or for IOs, or for analog design, different MOS transistors exist. Okay, there won't be one NMOS and one PMOS transistor. So corner lots will be different, and it doesn't mean that one corner lot correspond to only one type of NMOS and PMOS. It will be consisting naturally of different types of NMOS and PMOS condition. Okay, so here this NMOS may contain 2.5 sigma of NMOS, and this can contain minus 3.5 of PMOS. Here this can contain 1 sigma of NMOS and 3 sigma of PMOS. Like that, different scenarios can exist in these wafers. So that is the advantage of the corner lots, and by using these corner lots, the design weakness or the process weakness can be figured out, and thus while improving these defects, either the process defect or the design flaw can be corrected, and finally once the new round of fabrication is made, it will have less defects, and hence it will yield more wafers.